Hello.
Yeah, hello.
Can you hear my voice?
Yes, yes, yes. We are able to hear you. In just another 2-3 minutes, we will try to start the program.
Yeah, sure.
Yeah, thanks.
Yeah, hello everyone. I welcome you all to the today's session of short-term course on emerging technologies in processing of advanced materials and its characterization. I would like to introduce today's speaker, Mr. Dr. Gudpadi Venkatesh, Assistant Professor in National Institute of Technology, Warangal. Dr. Gudpadi Venkatesh received his Masters in 2010 and PhD in 2015, both from IIT Roorkee. He had a post-PhD experience as an assistant professor at BITS Pilani, UAE campus for 2 years. He has published various research articles in various peer-reviewed journals, conferences, a book chapter, and also filed a patent. He is guiding two PhD scholars and also guiding 5 ongoing MTech students and 4 submitted MTech students. His research interest includes abrasive flow machining, magnetic abrasive finishing, non-traditional manufacturing processes, micro material processing, hybrid machining, advanced manufacturing processes, and surface engineering. So we would love to hear from you, sir. So the stage is hand over to Dr. Venkatesh, sir.
Thank you. So, good afternoon, one and all. I would like to share my screen.
Narendra, sir, you stop sharing your screen so that
Yes,
sir
sir.
can
Yes.
share. Yes, sir. Venkatesh, sir, you can now share your screen, sir.
Yeah, sure. Are you able to see my PPT?
Yes, sir.
Yes, sir. Yes.
So, good afternoon once again. Thanks for giving me this opportunity. Uh, After my MTech, I worked in RGUKT. It's a wonderful college. I enjoyed a lot. I enjoyed each and every moment while working at RGUKT. And after that, I completed my PhD, and right now I'm in NIT Warangal. So I always feel happy to share my knowledge or to share my experiences with RGUKT associated. Thank you, Mahesh, and the other organizers. Yeah, let me start.
Yeah.
So my topic is about abrasive flow machining and its variants. So abrasive flow machining is one of the non-traditional finishing process which is used to finish integrate geometry up to nano level. So there are two things here. One is finishing integrate geometry and the two finishing up to nano level. So wherever you require high-end finishing for complex geometries like micro holes, micro slits, micro channels, and the complex profiles like turbine blade and internal finishing of nozzle or any complex geometry, and also if you want to finish multiple holes at a time, then abrasive flow machining is employed. So this is one of the non-traditional finishing process. So today's my lecture consists of introduction to AFM, working principle of AFM, general process parameters involved in AFM process, limitations of simple AFM or conventional abrasive flow machining, and what is the need for hybridization of this AFM process, and different hybrid abrasive flow machining processes. Finally, summary of all hybrid AFM processes, research potentials, conclusions, and references. So this is the plan of my presentation today. So let me explain you the principle of AFM. So principle of AFM is very simple. So one can develop this setup in our in a laboratory scale, in our workshop, in the machine tools lab or in a workshop we can develop. So, but its functioning, its capabilities are really amazing, you can see. So the principle is very simple here. Pumping an abrasive laden medium through or over the component to be finished. And the medium is pushed by means of two hydraulic cylinders. So here in the figure you can see, this is the hydraulic cylinder 1 and this is hydraulic cylinder 2. So these are connected to hydraulic setup. So hydraulic setup. So we require two hydraulic cylinders placed opposite each other, and in between we have a tooling. So we call this part as tooling or fixture. So this is tooling or fixture. So the purpose of this tooling is it holds the workpiece and also it guides this abrasive laden medium to and fro passing through the target surface. So here in the figure you can see this is a workpiece here and which is fixed in the tooling. So workpiece something looks like an external surface and it's a turbine blade. You can see some complex geometry involved in it. So the function of this tooling is it holds the workpiece and as well as it guides the medium to pass through the target surface. If you take inset of this workpiece, so this is inset. So what is observed here? So the abrasive laden medium consists of abrasive particles and also mixed with viscoelastic carrier, and this viscoelastic carrier will carry the abrasives and abrasion will take place. So the microplugging and abrasion will take place, and the polishing media, the medium which is mixed with abrasives will abrade the target surface and the finishing will take place here. So this is a principle. The principle is simple. So the process consists of two hydraulic cylinders and two medium cylinders. So these are medium cylinders where we fill the medium. So here the term medium or abrasive laden medium is used throughout the presentation. The meaning is here the medium is nothing but it's a tool. For example, in grinding machine, grinding wheel is a tool, right? And in lathe, single point cutting tool will act as a tool. And in milling, multi-point cutting tool is a tool, right? So similarly, in this process, we use a medium, abrasive laden medium as a tool, and it is flexible in nature, actually. So the main key element of this process is this medium. So the medium which is used in this process will plays a key role. And the second important part is the tooling, so which enables you to fix the workpiece and also to guide the medium to travel towards the target surface. The third part is, of course, the setup where you can control the number of cycles, extrusion pressure, and many other parameters. Yeah. The principle is first you will fill the medium in medium cylinder. So this is medium cylinder 1 and this is medium cylinder 2, say. So first you will fill the medium, semi-solid medium in one cylinder and you pressurize, you apply pressure using the extrusion pressure using the hydraulic unit and pumping the medium from one cylinder to another cylinder. So that is considered as one cycle. So during this process, the medium will travel through this tooling and abrades the target surface and starts finishing the target surface. So this is a principle. So pumping the abrasive laden medium from one cylinder to another cylinder passing through the target surface, and that one means once the medium travels from one cylinder to another cylinder, it considered as one cycle. So if you increase number of cycles, your finishing also will increase. Now let us see what is that medium and in detail about the medium. So medium is the most critical component in this process. So it is a combination of viscoelastic carrier with special rheological properties. So this is the viscoelastic carrier. This is something like a silly putty which we use for manufacturing of toys, and also it is something like rubber, natural rubber, which is available, and also you can make some synthetic rubbers from the company, and it consists of some special rheological properties, and it is viscoelastic polymer, means it's a polymer with some special rheological properties, means it is spillable in nature, means if you put this rubber, if you put this polymer in a glass, it occupies the glass shape, and if you put this polymer in a plate, it occupies the plate shape. So it is spillable in nature and flexible, very, very flexible. And we combine this polymer with special rheological properties with abrasive particles. So generally general used abrasive particles are silicon carbide, aluminum oxide, and also we use diamond powder for finishing high-end, means for finishing advanced materials. So you can see some realistic image where we prepared abrasive medium with these special rheological properties. So commercially available polymer, we call it as polyborosiloxane. It is made of silicon oil mixed with some chemicals. So that will behave like this rubber, means viscoelastic in nature, and this kind of behavior material is mixed with abrasive particles so that it will become a carrier for removing the material, and it can also travel the complex geometries, and also it can travel the integrated geometries, etc. And fine geometries, means small micro slits, micro holes. For example, if you take a needle, and if there is a we all know that there is a small hole in the needle, right? If you want to finish that small hole also, this is possible. So that small micro holes also can be finished. So AFM can be used for finishing, deburring, and radiusing. So it can be used for finishing, deburring, and radiusing. Means if you want to remove the burrs, you can use AFM process, and if you want to radius the already existing hole, then you can use this AFM process, etc. So far we have discussed the principle of AFM and the main parts like the medium, tooling, and as well as the machine. So just in the working video, you can observe the behavior of the medium that I am talking about. So you can see the behavior. So viscoelastic polymer mixed with the abrasive particles, you can see, and here you can see they are pressurizing the medium, and they are applying certain extrusion pressure for cleaning the manifolds which are used in the automobile components in this video. So there are several grades of abrasive particles with different mesh size. So this is the polymer medium I am talking about, and this is after machining, and this is before machining. After machining, you can observe that it will degrade. It will be degraded after machining, after doing proper abrasive. So these are the abrasive particles I am talking about. So several grades are available at different mesh, like silicon carbide, aluminum oxide are very commonly used abrasives. So mesh size, concentration are some of the parameters, important parameters which influence the finishing. So these are fine silicon carbide particles. Yeah, here you can see the performance and where actually this is applied and what is the actual function of it. So here, the medium is extruded by applying certain pressure, And the workpiece is this here. In this video, the workpiece is a manifold, and you can see the media is extruded. The media is extruded from the holes. We can say these are complex holes. These are not easy to finish using grinding, or it is radiusing the holes, and the metal which is removed from the workpiece is again mixed with this abrasive laden medium. Yeah, so this is the final output. You can see the finishing before and after. So we all know the function of finishing, right? So if the finishing is good, then the fatigue properties, creep properties will increase, and also the functionality of the product will increase. And when parts especially used in automobiles, which are subjected to continuous loading, or the parts generally used for medical implants, etc., where high-end finishing is required, finishing up to nano level. So this process is very much applied. So here you can see the finishing before and after. So here you can see that there are multiple holes, and holes are not, you can say, irregular shape holes, and the finishing at a stretch, and also radiusing and removing of burrs at a time. We can we can do it using AFM process. So this is one of the advantage, you can say. Yeah. So coming to next important part, I already discussed, that is tooling. So tooling is one of the important part. So it is generally for internal surfaces, and for external surfaces we need to develop a separate tooling. So here you can see, so this cylindrical bush. So our target is to finish the internal geometry of this cylinder workpiece, and these are the tooling. So these are used to hold the workpiece and as well as to guide the medium passing through this target surface. And this picture you can see, this is for external surface. So we developed this for hybrid AFM process that we'll be discussing in another next slides. So in this process, like we have a restricted passage in order to get advantage of pressure and velocity changes, and also we got better finish by restricting the passage of medium, so that there will be more pressure applied and more finishing will take place. So these are this material generally we use is nylon and Teflon materials for developing this tooling in order to finish the external geometries and internal geometries. Yeah. So generally the various applications include turbine engine parts, medical implants, automotive components, die polishing applications, and aerospace applications, etc. AFM is very commonly used. What are the main important parameters in AFM? As I said, machine and medium and tooling, right? These three are the main parts in AFM, right? So machine related parameters are, so we can control extrusion pressure, we can control number of cycles or processing time, and we can control flow volume and its speed by using the machining setups. And abrasive medium related parameters are medium viscosity. As we are using semi-solid medium, the medium viscosity plays an important role in finishing. Medium rheology, abrasive type, size, and concentration we are using for machining, for finishing. And tooling, the workpiece configuration, restricting passage length and area. As I said, if you restrict the passage, then the pressure applied and the velocity, there will be change in the pressure applied and velocity, and that gives rise to change in the finishing area. Next is workpiece hardness. So these are a few important process parameters in simple AFM. Yeah. So what are the advantages and limitations of traditional AFM process? As I discussed, the major important part is to finish inaccessible areas. Like we have seen the finishing of manifold in the video. which is a part of automobile car. So how to finishing inaccessible areas. Like you can also finish a internal dimension of a nozzle. You can also finish a turbine blade. You can also finish a blind hole, right? So there are many advantages using AFM, which cannot be done by using traditional finishing processes such as honing, lapping, and grinding, etc. Right? And another advantage is complex internal passages of components, and it saves up to 80% cost of final finishing component comparatively manual and easy to operate. Component can finish with high tolerance. So these are the advantages. And what are the limitations? One of the limitation is low material removal rate and low finishing rate, and it increases the processing time, right? So even though AFM is very good process which can finish inaccessible areas and complex geometries, etc. But however, it suffers with low finishing rate and low material removal rate. Means it is taking a lot of time to finish. Means the number of cycles required is more and more. So in order to overcome that, many people started thinking hybridizing the process. Now let us see why the hybridization is required. So we all know hybridization is a combination of two or more non-conventional processes in order to take the challenges, right? So why hybridization is required? So combining two or more processes in order to get advantage, which otherwise is not required, right? So if you are combining two or more processes, if there is any advantage, then it is means it is valuable. The process is valid. So why we require these hybrid AFM processes? So finishing of surfaces of advanced materials. Nowadays, in the market you can see a lot of new composites have come, and slowly the automobiles, like initially they are using steels, and steels are replaced with composites, and in many areas composites are replaced by metals, and as well as you can see the advanced materials such as super alloys like nickel based alloys, Inconel 718, 738, heat treatment applications. Inconel generally used for rocket engines and turbine blades, etc. So these super alloys are very important, and they have a lot of applications. Finishing of them is also one of the important criteria where the high-end finishing may be required when these super alloys are manufactured for rocket engine or turbine blades, etc. Then abrasive flow machining can be hybridized or can be improved in order to finish these advanced materials. Next, finishing up to nano level. So initially AFM is used to go up to micro level, and that can be go up to nano level, Armstrong level as well nowadays. So they are working on reaching nano level and Armstrong level. So improving the efficiency of the process and to achieve higher material removal rate. So these are the reasons why people started developing hybrid AFM processes. And what are the literature available? What is the literature available on AFM and hybrid AFM? So we all know now what is simple AFM and what is the advantage of it, and what is the difference, how it is different from the other processes, what are the important parts, what are the process parameters, and what are the applications and advantages. Let us see what is this hybrid AFM. So hybrid AFM is further divided into magnetic based AFM, chemical based AFM, centrifugal based AFM, rotational based AFM, and ultrasonic based AFM. Hybridization means we all know combining two or more energy, two or more sources in order to get an additional advantage of it, in order to get benefit of by combining these processes, right? So again, this magnetic based is further divided to magnetic assisted abrasive flow machining, magneto-rheological abrasive flow machining, and chemical based electrochemical machining, and centrifugal based spiral assisted abrasive flow machining, centrifugal assisted abrasive flow machining, and rotational based, like we have rotational assisted abrasive flow machining, and ultrasonic based we have ultrasonic assisted abrasive flow machining, ultrasonic flow polishing. Now let us see one by one, and what is the advantage of this process, and what is the principle of these processes, and how the finishing rate has been increased, and how the material removal rate has been increased using these processes. We'll discuss. First, in Jones and Hulls in 1998, he has introduced ultrasonic flow polishing. Actually, AFM is first developed in 1960s by Extrude Horn Corporation, USA. Right. After that, the first variant is in 1998. So he has incorporated AFM by combining with USM, and he called it as ultrasonic flow polishing. So it is a combination of AFM and USM. And in this process, the abrasive polymer mix is pumped down the center of ultrasonic energized tool. So what he did is, so he has used the ultrasonic tool, which we generally use in USM process, and the ultrasonic vibrations are given to this tool, and they use generally ultrasonic means 20 kilohertz and more than that. So they apply this ultrasonic vibration to this semi-solid medium, and here you can see the hole is a blind hole. So it is not a throughout hole, and this ultrasonic energizer is having some hole here. You can see where the media will come out. Once you pressurize, and the media will come out from this passage. So this is the passage for the media to come out. The principle is simple. So he has pressurized the medium using an extrusion pressure, and as well as using an ultrasonic tool, he actuated the medium. And he energized medium by using this ultrasonic vibration, by giving ultrasonic vibrations to the medium. And he achieved better result compared to simple AFM. And also he has recorded better material removal rate compared to simple AFM in his research work. Next, magnetic assisted abrasive flow machining. In the year 2002, so one scientist, one researcher, Sage Paul Singh, has developed this magnetic assisted abrasive flow machining. So in this, the major input and the major breakthrough in the research is, basically we all know now what is the principle of AFM. So this is the hydraulic cylinder 1, and this is hydraulic cylinder 2, and this is the medium cylinder, right? So up to here is fine. They are pressurizing the medium from one cylinder to another cylinder, passing through the target surface, everything is fine. But the advantage means the enhancement of this process is here. Here you can see he applied magnetic field around the tooling. So this is the tooling, and he applied magnetic field around the tooling, and he has used iron carbon particles along with the silicon carbide, and he mixed the medium with iron carbon particles and silicon carbide. When electromagneticity is applied, then these iron carbon particles are attracted towards the magnetic field, and there is more interaction of abrasive particles towards the asperities, and there is more scratching takes place, more microplugging takes place, and more machining takes place, and which leads to less finishing time, or less finishing time. That is the major difference he has observed, and he has recorded better finishing and also better removal rate compared to simple AFM process. So these are few scanning electron microscopic images. He has worked on both magnetic materials and as well as non-magnetic materials, and he has shown the finishing aspects in terms of microscopic images using scanning electron microscope for different materials and different process parameters and levels. The another scholar, Ja and Zain, in the year 2004, so he has extended his studies on magnetic assisted abrasive flow machining by studying the magnetorheology of the medium. So the principle is same here. So applying the electromagnetic field here, and we have an hydraulic unit controlling pressure and other parameters, and we have flexible medium which is used to pressurize, which is used to flow from one cylinder to another cylinder. So we have a fixture which holds the workpiece and which guides the medium to target, to pass the medium to the target surface. So everything is same. So magnetic field is applied using electromagnet coils, and the difference is here you can see. So due to the magnetic field applied, the CIP chain formation has taken place, and which improves the active abrasive grain density in this process. If the abrasive grain density increases, then the finishing rate also will increase, right? The logic is here is, so once the magnetic field is applied, the carbon iron particles will surround around the abrasives. So these are the abrasives. So these are the abrasives, and the small particles are the carbon iron particles. And when the magnetic field is applied, so these magnetic particles surrounded the abrasive particles, and they are attracted towards the tooling where the magnetic field is applied. And due to this chain formation, the axial force applied to the abrasive particle for finishing the asperity has been tremendously increased, and active abrasive grain density also increased. Means the participation of abrasive particle, means for example, if you are not applying magnetic field, this abrasive particle, so this is our workpiece, right? So this is our workpiece. So say we have some asperities here, right? So this is our workpiece. Say this is a cylindrical bush. We have some asperities here, right? And this is the abrasive particle, say, and these abrasive particles are surrounded with the silicon carbide. So due to the applied magnetic field, you can observe that the interaction of abrasives has been increased. If the magnetic field is not applied, these abrasives may simply slide and roll without touching the asperity. So that particle we call it as inactive particle. And the abrasive particle which touches the asperity and which cut the peaks, we call it as active particle, right? So every scholar tried to improve the active abrasive grain density. Means he tried to improve the active particles by combining this energy, by combining these sources. Like in this case, he has combined the electromagneticity, right? Yeah. So here you can see the abrasive particle and the chip flow direction. So this is the asperity I'm talking about. So this CIP chain will help you to increase in the axial force as well as the radial force. So the resultant has been increased, and you can see the microchip cutting of the abrasive particle with the surrounding iron carbon particles, which leads to higher material removal rate and also high finishing rate. Yeah. Next is called rotary abrasive flow machining. So he has used one spindle, and he has inserted in the medium, and he rotated that spindle, right? So the other principle is simple. So it consists of one hydraulic cylinder, two hydraulic cylinders passing through the medium from one cylinder to another cylinder. The remaining principle remains same. And the difference is he has used one spindle, and he rotated that spindle, and due to this rotary action, so the protrusions of the abrasives are everywhere, and also the abrasive interaction with respect to asperity has been increased due to this continuous rotation of the spindle, which is connected to, which is inserted into the medium. Next, another scholar in the year 2006, so he has introduced a centrifugal force. So this is one of the tricky process. So you can see here he has designed a lot on the tooling. He has designed a lot on tooling. He has not used any magnetic field. So he designed a lot on tooling. He developed a special tooling for this centrifugal assisted abrasive flow machining, and he has introduced centrifugal force around the tooling, and due to that centrifugal force, the abrasive interaction with respect to asperities has been increased. So the figure shows the centrifugal assisted AFM process. So here we have one cylinder, and this is another cylinder, and this is the tooling. This part is tooling, and this is the centrifugal rod, right? So how he has generated this centrifugal rod, and how he has rotated the centrifugal force, etc., we'll see now. Yeah. So this is the fixture I'm talking about. So this is a special fixture developed in order to create a centrifugal force around the tooling. So these are the two nylon fixtures, and this is the gear train, and this is the centrifugal rod. So this fixture will be useful when this centrifugal rod is inserted into the workpiece actually, right? And this centrifugal rod is inserted into a cylindrical bush workpiece, and they rotated this centrifugal rod, right? They rotated this centrifugal rod, and due to the rotation of this centrifugal rod, centrifugal force has been generated, and there is more concentration on the abrasives, right? There is more concentration of abrasives towards the target surface. Here you can see. So this is the centrifugal rod I am talking about, right? And this is your workpiece, right? And they rotated this centrifugal rod. Centrifugal force has been generated, and due to that, there is more interaction of abrasives towards the asperities, and the finishing rate has been increased, and the material removal rate also improved compared to simple AFM process. So these are few scanning electron microscopic images that are working at different levels using different abrasive particles and different micron level abrasive particles. Yeah. Coming to next, drill bit guided abrasive flow machining. So in the previous case, we have seen they are using centrifugal rod, right? So one important thing I forgot to tell is they changed the shape of the rod, and they have explored the effect on finishing as well as the machining. And also they varied the speed of the centrifugal rod in RPM. They explored the variation in finishing and material removal rate. In the previous case, magnetic assisted abrasive flow machining, they explored on magnetic flux density. They changed the voltage. By changing the voltage, they have explored finishing rate and as well as material removal rate. So for every hybrid process, if you observe, so there are some new parameters introduced. Those parameters we call it as hybrid parameters, and the influence of these parameters will be novelty in the field. Yeah, drill bit guided. So instead of centrifugal rod, so here in this process they introduce a drill bit into the medium. So what happens if you introduce a drill bit into the medium? When AFM is on, when you are pressurizing the medium from one cylinder to another cylinder, when AFM is on, what happens? So just assume this is our workpiece. So workpiece, and here we have an asperities, and here we have an asperities. So our target is to finish this. Say we have introduced a drill bit here. Yeah. So then what happens actually? So drill bit guided abrasive flow machining. So we all know that the helical flute structure of the drill bit, how it helps in AFM. So the flow along the flute path. So when you are pressurizing the medium, the flow along the flute path and the reciprocating axial flow and the scooping flow. So these three are possible when you are inserted a drill bit inside the AFM process, when you are working on cylindrical bush, when you are finishing a cylindrical bush. And for example, so if you are not inserted a drill bit, for example, then the particle will simply move in one direction, right? The particle will just move from one cylinder to another cylinder. Maybe some particles may hit and some particles may simply slide and become inactive. However, if you insert this drill bit, then due to the helical flute structure of drill bit, the flow along the flute path is possible, and the reciprocating axial flow is possible, and the scooping flow is possible, and which leads to more interaction of abrasives with respect to asperities, right? So our target is to improve the finishing rate and to improve the material removal rate and to work on advanced materials, right? And also, if you observe, by introducing this drill bit or centrifugal rod, the passage is restricted, right? So if the passage is restricted, then it increases the finishing, because if the passage is restricted, the medium is pressurized to flow on the target surface. If the more pressure is applied, vice versa, then there will be more cutting action and more finishing action. So these are the possible things. These are happen actually while working on drill bit guided abrasive flow machining. So another scholar, Shankar et al., so he has rotated the entire tooling. So the complete tooling has rotated by using a separate motor. He has rotated the entire tooling. So due to the rotation, actually, here you can see what he claimed is the helical path followed by active abrasive grain along the workpiece surface per stroke for different workpiece rotational speeds. So here you can see at 2 RPM, 4 RPM, 6 RPM, 8 RPM and 10 RPM. So the helical path followed by the abrasive. So if you are not rotating, for example, then there won't be any helical path, and there won't be any any separate action. Only there will be a to and fro action, and due to that, maybe some particles may be active, some particles may not be active, and it takes a lot of time for finishing. But however, if you are introducing such mechanisms such as uh, rotating the rotating this workpiece tooling, or introducing a drill bit, or introducing a centrifugal rod, or changing the shape of the rod, or introducing the magnetic field around the tooling, right? So all these hybridization helped AFM to improve its finishing rate. Let us see the next scholar in the year 2010. So he has introduced spiral flow assisted abrasive flow machining. As we discussed in the drill bit guided assisted flow machining, so he has introduced the drill bit, but he has not rotated the drill bit. Whereas in spiral flow, so he has introduced the drill bit in the workpiece zone, and also he has rotated. So this rotation of drill bit will help like a flushing element, and it energizes the abrasive particles inside the medium, and as well as it will gives you the scooping flow and also helical fluid flow, etc. Right? So here you can see this is the workpiece, and one more thing you can observe is this is horizontal AFM. So far we have seen vertical AFM. This is horizontal AFM. So horizontally two hydraulic cylinders are placed. So this is one, this is two, and this is the medium. This is the flexible medium we are talking about. This is the drill bit. So this is the gear train. So using that we can rotate the drill bit. So what he claimed is actually, so instead of simply putting the drill bit, so if you rotate at certain RPM, optimum RPM, then there is a centrifugal force generated, and also this scooping flow and helical flow of the drill bit help a lot, and there is active abrasive grain density, and the restriction of passage is also possible here by introducing all this drill bit inside the workpiece. And our target is to finish this integral bush. That is successfully done by using this spiral flow assisted abrasive flow. And another important process is ultrasonic assisted abrasive flow machining. So here also you can see the horizontal AFM process, and these are the hydraulic cylinder 1, this is hydraulic cylinder 2, this is medium cylinder 1, you can say, medium cylinder 2, and this is our tooling. Yeah. So what is done in the UFM process is, so using an piezo actuator, vibrations are given externally to the workpiece. So if you remember, in ultrasonic flow polishing, which is one of the first variant, so in ultrasonic flow polishing, we energize the medium using the ultrasonic horn. Whereas in UAFM process, ultrasonic piezo actuator is used to energize the workpiece to give vibrations externally to the workpiece. And due to these external vibrations, the active abrasive grain density has been increased because the vibrations are given perpendicularly. So for example, here you can see the media flow direction is this way. So media is flowing to and fro in this direction, and while media flow direction is on, then we are vibrating the workpiece perpendicularly to the flow direction, and but what happens, etc., we'll see in the next slides. What happens if you vibrate the workpiece externally when the AFM is on. So this is developed in IIT Roorkee. So here you can see first the design model is developed. So here you can see the medium. Yeah. So this is a 3D model developed in SolidWorks. So here you can see the piezo actuator, how it is mounted and how the workpiece is vibrated. And similarly, parallelly, how the medium is extruded from one cylinder to another cylinder. So here in this case, the vibration in axial direction parallel to the media flow direction. So by mounting the actuator in axial mode, so we can vibrate in axial direction as well. So this is a model we have developed, and after that, the setup we have developed in IIT Roorkee. Here you can see this is the function generator and KC-N15 amplifier. These amplifiers are for giving vibrations. So we have a piezo actuator. So this is the hydraulic cylinder I'm talking about, cylinder 1. This is a medium cylinder. This is the tooling I'm talking about, and this is the actuator. And here you can see the medium which is collected, which is leaked from the piston. You can see from the fixture. So you can see how the actuator is mounted and how the medium is pressurized. Piston, and the green color part is the medium cylinder, and this is the medium collected here. So the additional thing we are doing here is we are vibrating the workpiece externally when the AFM process is on, right? When the 2 and 4 AFM process is on. Yeah, let us see what happens if you vibrate the workpiece. Why actually the surface finish is increased, and why the finishing rate has been increased, why the material removal rate is also better compared to simple AFM process. So let us take a simple schematic illustrations. This is a cylindrical bush. So this is a cylindrical bush, and our target is to finish this internal geometry of the cylinder. And these are the say asperities. These are the asperities of the workpiece. And remember that we are working on a finishing process. So the initial roughness we consider itself will be 1 micron or less than that. And we reach up to nano level by using this advanced finishing processes. It means we can't take the rough surface. We can't take the very rough surface, which is say 10 micrometer, 20 micrometer like that, because there are many other processes to finish that rough surfaces, and also while manufacturing itself, we take utmost care to get a near net shape product, right? These processes are the secondary processes which can finish up to nano level for certain applications, right? So when simple AFM is done without vibration, then some particles will have, every particle like flowing media flow direction will have some axial force, and also the properties of the medium which are viscoelastic in nature, which are having special rheological properties, will have certain radial force, right? Whereas there are some particles which may be inactive, which may simply roll and slide, and which may not contribute in finishing the surface, right? So in the second case, so if the ultrasonic vibrations are introduced, so here you can see the particle is hitting at an angle theta, and it is unidirectional when the vibrations are incorporated externally to the workpiece. And here you can say the axial force and the axial velocity has been increased, and as well as the radial force has been increased, which result into the increase in the resultant force. This is due to we are vibrating workpiece externally and also perpendicularly to the media flow direction, right? So in the third case, here you can see the rising of and a receding of cycle. So we use the sinusoidal wave, sinusoidal vibrations we have incorporated while finishing. So at different levels, we have a rising of, receding of, means we are converting these vibrations into mechanical, right? So the electrical energy is converted to mechanical by using this piezo actuator. So how it will help in finishing? So the fourth figure you can see that the abrasive protrusions are everywhere. Abrasive protrusions are everywhere throughout the surface for finishing and for removing the material, right? So let us see now the other figure. So with and without vibration. So this is without vibration. So this is without vibration. This is with vibration. So what happens actually? So in case A, if the vibration is not given, then we can say that this is a simple AFM. In case B, if the vibration is not given, you can see a slight enhancement of the asperities because your workpiece is vibrating at high frequency and there is certain amplitude, say 10 micrometer amplitude. So the enhancement of the asperities in the rising of and receding of will leads you to certain change in the distance, that amplitude, right? Due to that, the abrasive particles which are inactive will also become active due to the enhancement. Say for example, this particle may not be active here, whereas due to the vibrations given to the workpiece, so the inactive particles are also becoming active, and also the particle is hitting at an angle theta and they are traveling in unidirectional because of the vibrations given externally to the workpiece. So there is more active abrasive grain density. Means there is more interaction of abrasives towards the asperities, and that is the reason the finishing rate has been increased, and also the material removal rate is also better compared to simple AFM process. So in the another study you can see the abrasive asperity peaks and the interaction of abrasive with respect to asperity peak and with some proof. So the figure F, if you see, the microchip has been removed from the surface by using UAFM process, and it is captured by using atomic force microscopy. And the figure G, you can see how the microchips are removed from the surface by using optical microscope result. And these are correlated with respect to the schematic illusions of UAFM process, right? So this is another case. This slide shows the axial direction. So when the vibrations are given in axial direction, in the previous case, we are vibrating the workpiece in radial direction, and we have recorded the changes of the cycle, sinusoidal cycle, and we have recorded how the abrasive and the asperities are interacted, etc. Whereas in this case, when you are vibrating the workpiece in axial direction, what happens actually? So here you can see the advancement of the asperities, means the asperities are advanced and then they are coming back again in this 10 amplitude, whereas the abrasive particles are also becoming more active, and the finishing rate is further increased using this axial mode of UAFM process, whereas material removal rate is much better in radial because the radial force will leads to material removal, will leads to the more indentation of the abrasive particle and the asperity on the workpiece surface. So for better removal rate, radial mode is suitable, and but for better finishing, the axial mode is suitable in UAFM process. So we have done few simulation studies in AFM process by using by doing CFD analysis of medium flowing inside the workpiece. How the pressure distribution, how the velocity distribution, and how the temperature distribution will take place when the workpiece is subjected to vibration. Why? Because in simple AFM, we all know that how the pressure distribution takes place and how the temperature of the medium will behave, and also we all know the pressure velocity distribution. Whereas when you are changing the technology, when you are advancing the technology by adding to or more another processes, when you are hybridizing the process, then it's a obvious need that you need to understand the analysis part. So how the temperature will behave, how the velocity and the pressure will vary when you are subjected to the workpiece to vibration. So these are the few medium properties and the parameters we incorporated for simulation purpose before doing the experimental. So this is the grid independency test. So for using, and you can see the number of elements used, the grid sense, the pressure applied, the size, shape of the grid used, everything are given here. The number of nodes, number of elements used, type, tetragonal, cubic, and element size, number of equations. So all those things are given. So this part, basically, this part is simulated, and main concentration is this. Okay. So we concentrated how the medium behaves. So this is the workpiece actually, workpiece which is in vibration. So this is the workpiece which is in vibration. We concentrated on how the media behaves, how the media behaves inside when the workpiece is vibrated. So here you can see we have recorded some video. So workpiece when it is vibrated externally in radial direction in the figure 1, and the workpiece when it is vibrated in axial direction. So in the simulation we have understand that there is no much influence on the amplitude. So we worked on different amplitudes, and we observed that there is no much influence on pressure, velocity distribution by varying the amplitude. However, the vibration given to the workpiece has a lot of influence in pressure distribution and as well as velocity distribution and temperature. Temperature, there is no much change. So why we bother about temperature is generally when the temperature increases, we are using a semi-solid media, then the stability of the media goes down, right? If the stability is not there, then the particles present in the media may not be active. So that's why the thermal degradation of the media is important. Thermal stability of the media is important. So for that, actually, we have done simulation and also we correlated with some experimental result as well. So this is the present slide shows the pressure contour, the pressure distribution in AFM process, and the velocity distribution here you can see. So three different like simple AFM and with ultrasonic vibrations and with different amplitude you can see. And you can see that blue and red are matching. It shows that there is no much change if the amplitude is changed. Whereas you can see the difference from the black line and the blue and red line. It shows that there is difference. There is difference by giving simple AFM by without vibration and with vibration. There is some difference in velocity, pressure, etc. So this is the contour of velocity. So here we have slightly correlated the protrusions of abrasive particles, and we have correlated the results we got from the simulation. So here you can see the velocity vectors hitting at an angle theta, and similarly you can observe the abrasive scratches on the workpiece, the tendency of hitting of an abrasive particle at an angle theta. So the temperature, why we use this temperature is generally, as I said, if you vibrate the workpiece externally at 20 kilohertz, we are curious to know whether any temperature is increased. But we understand that there is no much change, the increase of temperature. So the process is safe. We can vibrate the workpiece while doing AFM. So we have studied a comparison between the temperature distribution of media result and as well as the thermogravimetric analysis of medium. And we also done on one external workpiece. So whatever we have seen now is while working on a cylindrical bush, and now these are on a bevel gear. So we have developed one fixture for bevel gear, and we took bevel gear because it has some complex geometry, and the finishing of bevel gear is not that easy. So there are only few processes such as like gear hobbing and electrochemical honing, etc. So they make one dummy bevel gear, and they contact this workpiece bevel gear with the dummy bevel gear, and they do electrochemical honing, right? So AFM is also one of the alternate process for finishing gears. Like you can finish helical bevel gears, you can finish bevel gears. Only thing is you need to develop a proper tooling, proper suitable fixture for your bevel gear. And then we have developed some studies on how the media will behave on a bevel gear, like velocity distribution, pressure distribution, and also the temperature distribution. So these are the comparative studies you can see before and after UFM process. So boring marks on the cylindrical bush and finished glaze surface is observed, and these are also few morphologies we have collected before and after finishing, UFM process using AFM and comparing them with UFM processes. Next, one important case study I would like to present here is, so while working on bevel gear, so we can see here how the design of the fixture inside the bevel gear. So here you can see it is in taper, and here you can see there are some holes where we are guiding the medium to pass through this bevel gear teeth, and also the small hole in the fixture, and how we incorporated the vibrations to the bevel gear, and how we have given the amplitude, how we have designed, and how we have taken care to leakage of the medium, and all these are tricky in the process, right? The remaining process is like the AFM will be on, and also will vibrate the workpiece externally, and there will be obviously of abrasive laden medium on the workpiece, and also you can remove the burrs, etc. So we have one small study we have made. So by using UFM and AFM, so here without vibration, so that is simple AFM, and with vibration. So we have selected 19 kilohertz as the optimum vibration by using the pilot experimentation, and 10 amplitude we have fixed because it's a constant here, because in simulation we observe that changing the amplitude is not giving much difference, and here it will be 0, and the extrusion pressure applied in bars, so we have taken 30 bars, and we kept this constant for both cases, and processing time also we kept same for both cases, like 5, 10, 15 UAFM and 5, 10, 15 in AFM process. Media flow rate is kept same. Abrasive size we use same for both the UAFM and UAFM. And abrasive concentration is 60% of abrasives are present in 100% of abrasive laden media. Means the another 40% is the viscoelastic polymer and also the polymer gel, which is mixed with the abrasive particles. Media viscosity is measured, so 730 Pascal second, based on the pilot experimentation we have to. So what interesting result we found here is, so our main outputs are surface finish improvement. So we are finishing the surface up to nano level, the micro level, nano level, and the another output is the material removal, right? How much material is removed and how the material removal rate will take place, right? So this black color line shows a simple AFM, and this shows UAFM. Right? The interesting study is like when I'm working on AFM process, I observed that at 5 minutes there is 35% improvement of surface finish when I checked before and after. And at 10 minutes, there is some 50% of improvement. Means 10 minutes means up to 10 minutes, like the cycles will go on, right? So there is a continuous cycles from one cylinder to another cycle. You are upgrading the target surface. I observed some 50%, and at 15 minutes, I observed that there is no much change. Like after 50% improvement in surface finish, I observed that there is no much difference, much change. It is only just 5% increase, even though I increased 5 minutes. Whereas when I started giving vibrations to the workpiece, the beauty is at 5 minutes itself, I could reach 60 plus percentage, which is not possible with 15 minutes, right? With 15 minutes of simple AFM, I could reach only 55, whereas I reached 65% of improvement of finishing using UAFM at 5 minutes itself. And after that, I could reach 70, and finally some 70 change have closed using UAFM process. But the beauty is the instant, means the finishing rate, how how 65% is possible with UAFM, which is not possible with AFM, even though for 15 minutes. So that is the beauty here. So we can say that the process is rapid because of vibrating the workpiece externally, and also the asperities, the abrasive particles in the medium are energized due to the vibrations applied externally. Similar result I have studied on the material removal rate, which is the second response in my case. So here you can see the slopes, and as well as here you can see the improvement for 5 minutes, how much material is removed in milligrams, and for 5 minutes, how much material is removed for UAFM cases. One of the interesting study I observed while working on UAFM and AFM process. So these are the few surface morphologies which are taken before and after processing using AFM and UFM. You can see the RA values also from the study which we have made. Here you can see the gear which is finished before and after finishing. So this is a rough surface which is observed on the gear, and deep feed marks are observed on the gear workpiece. And after UFM, you can observe some smooth surface finish on the gear. And we have taken a lot of various values at different levels, various values by using optical profilometer and as well as using ferrometer for taking the RA values. Right? We have used probe type as well as optical in some cases. So in the fourth case, you can see that the abrasive scratches, the reduced feed marks, the feed marks which are while manufacturing the gear were reduced, the abrasive scratches are visible, the finishing has been increased, and you can see that the surface has been improved, and that can be identified from the scanning electron microscope. Yeah, these are the few processes, and you can see from the literature like magnetic assisted, centrifugal force assisted, magnetorheological, spiral assisted, ultrasonic assisted, rotary assisted. So there are various processes, and still people are working on various variants of the process. But ultimately their goal is to improve the finishing rate and to improve the material removal rate, and also to finish the advanced materials to reach nano level and up to Armstrong level are the targets. So if I summarize the parameters, simple AFM process, the machining parameters such as extrusion pressure, flow rate, number of cycles, machining time or the number of process cycles, both are as same. So media parameters, viscosity, abrasive concentration, type, grain size and shape. The workpiece based parameters, we have material properties, workpiece geometry and size, and surface type of cooling. Coming to hybrid based parameters which are introduced. So we can say here magnetic flux density, current, case of magnetic assisted, and shape of the rod, rotation speed of the CFG rod in case of CFAFM. What they claimed is if the rotation increases in CFA process, the rod behaves as normal, means the shape is not much influenced. For example, if you introduce a drill bit to a cylindrical bush and if you want to finish the internal geometry of a cylindrical bush, then the drill bit with the help of that scooping flow and helical fluid structure, so there is some improvement and there is more interaction of abrasives towards the asperity. But if you rotate at a high speed, for example, then it acts as a normal. It acts as a normal rod. There is no that special structure will influence if you increase the speed. So that's why optimum speed is required, and they suggested better to go for lower speeds. Higher speeds, the rod will act as normal. There is no much effect of that scooping flow and the helical fluid. So drill bit guided AFM, the drill diameter. So they vary drill diameter, and also by varying drill diameter and speeds, they have incorporated results and as well as the metal. Next, rotary AFM process, the rotation speed of the workpiece. So they have rotated the tooling. So the rotation of the workpiece is here in this case, whereas the rotation of the drill bit is in this case, whereas the shape of the rod in this case, and magnetic flux density in this case. And ECFM, this we have not discussed so far. So they have covered and they have worked on current intensity and voltage and abrasive test use. UAFM, applications of vibrations radially and axially, and amplitude of vibration. So vibration frequency and the type of actuator, etc., for playing an important role in UAFM process. So these are few summarized the parameters which are newly implemented in AFM process and new variants in AFM process. So if you see the broad classifications of AFM process, so you can see the AFM in shop floor, so which is simple one way, two way AFM. One way means in the video we have seen. So one way we are pressurizing the medium in the working video. And the other way we are collecting the medium from the which is coming out from the workpiece. Right? Two way means we pressurize the medium from one cylinder passing through the target surface, and the other side also you will be collecting the medium in the other cylinder, and the process will continue. Orbital AFM, so we use some orbital vibrations for finishing this, and hybrid AFM like magnetic assisted, magnetorheological, ultrasonic flow polishing, centrifugal assisted abrasive flow machining, rotary assisted abrasive flow machining, ultrasonic assisted abrasive flow machining. So there are various variants, and for each variants, like you can see this, you can call it as a tree diagram. So what are the parameters acting for each variants are given here, and the process of parameters, input. So these are the input process parameters, and these are the output responses. So majorly people worked on surface finish improvement and metal removal. However, people also can work on surface integrity properties. They can work on cylindricity. They can work on removal of burrs, deburring. They can work on the flatness. You can check the flatness of the workpiece. One can work on residual stresses developed like after using UAFM process or AFM process. So there is a lot of scope in responses, in developing the responses. AFM. So if I summarize using author-wise and principle-wise, so here you can see different authors developed different processes. I have worked more on UAFM process. So different authors, like they have developed the principle and they have hybridized parameters like stage pulsing has worked on magnetic flux while finishing magnetic and non-magnetic materials. D.K. Jain et al. Worked on magnetic flux density and current. Dabrowski worked on voltage, current, like that. So I have summarized, like R.S. Valia worked on rotational speed of CFG rod, shape of the rods, etc. Bit guided drill diameter by varying the drill diameter. So there are various hybrid parameters which are summarized, and the workpieces used. There is workpieces used also recorded here, and abrasives used by the different authors, and the abrasive carriers used, the concentration of abrasives maintained, surface generated finally like after finishing. AFM, always there are two scopes. One is a product development and the other one is process development. Product development means the major parts of the product, the machine or tooling, and medium used, flexible medium, and the machining setup, right? So one can develop a new tooling, flexible tooling, which can be used for different materials, for holding different shapes, say internal and external. And one can patent a flexible tooling in the AFM process. And the other development can be, you can use different medium, right? In my case, I have used natural organic polymer and we have patented it, right? So instead of using a polymer gel, which is commercially available, so we have used a natural organic polymer containing these elements, and we have recorded better result compared to the commercially available medium. And this is the product development research in AFM field. So one can work on developing a new medium which having the viscoelastic polymer, viscoelastic rheological properties. And one can also think of developing a flexible fixture or a new design of fixture for holding workpieces in AFM and UFM process. So that is product development research scope. And process development, like you can see, whereas people have hybridized the process by incorporating AFM with ECM, AFM with MAF, and AFM with drill bit guided, AFM with ultrasonic mission. So one can think on incorporating AFM with other process that comes under the process development of research. So in my case, during my MTech, I started developing a product. We have patented it, and during my PhD, I started developing on a process, and we have incorporated ultrasonic vibrations externally to the workpiece. So like my contribution is towards the process is ultrasonic flow harnessing, and towards the product is developing a new rubber natural organic polymer based medium for finish. So like that, in any field, when you are working on any kind of problem like EDM or ECM or any other process, you have to, one can think on the contribution. What is the contribution you are giving to that particular area, particular field, either in terms of product development or in terms of process development. In order to do that, so you should have a command on the literature, what is going on in that field, either it is ECM or AFM or EDM, what is going on in the field, what is the state of art of such process till date, up to date, and what the researchers are doing, what are the limitations, what are the advantages. Once if you know the literature, once if you know the trend of the process, then you can implement your ideas and you can contribute in that field. That is what important while doing the research, in that particular field. So if I summarize the mediums used, like I said, we have developed this during my master's. So there are many people working on developing this medium, alternate medium, like Michael Carr et al. So they have used natural rubber. Some people they have used rubber in a form of milk. They mix that rubber milk with abrasive particles, and they use various gels to prepare the medium. And in my case, some people worked on wax. They use wax. They mixed with abrasive particles and they have tried. And some people just with simple chili putty have mixed the abrasive particles. So whereas people have developed like magnetorheological medium, polymer based fluids, So many organic and inorganic components they have mixed in order to get a better properties of the medium. Like that. So this slide shows the summary of different developed mediums in AFM. Coming to capabilities. So what are the capabilities? Like the main outcomes are machining, finishing, and as well as the material removal. So here you can see various authors worked on different materials, and they have achieved better surface finish and better RA. In our case, actually UFM, when we worked on Inconel 718, we achieved 0.09 micrometer surface finish and 10.93 milligrams of the material has been removed. Even though we can't compare with other processes because the material may be different, and they have used advanced material. But however, the finishing obtained by using UFM process is better as compared to the other processes. And also, we have some unique advantages using UFM process, such as in magnetic field assisted, you have to apply the magnetic field. In the ECM, you have to, for example, in CAFM and drill bit guided. So these are limited to cylindrical bush only. Why? Because for everywhere you can't insert the rod and rotate, right? So if you want to finish a turbine blade, you can't insert a centrifugal rod and rotate, or you can't insert a drill bit and rotate, right? A rotary AFM, for example, if your tooling is very big, then you can't rotate that big tooling. Whereas UFM means only thing is you have to vibrate, either it is a flat workpiece or complex geometry or external workpiece or internal workpiece. Only thing is you have to vibrate workpiece externally, right? How to vibrate that externally is a tricky part here. So in that case, it has a bit advantage compared to the other processes. So these are the application-based work done in AFM. For example, like some people work on removal of recast layer formed by using wire EDM microscope, and some people work on removing burrs on spring collets. Means these people they got the workpieces from the industry directly and they worked on it. So diesel flow injector nozzles are finished by using AFM, and channels and in laminated toolings are finished by using AFM, and for finishing helical gears. And in our case, we worked on finishing of bell gears, etc. So like that, application based also you can work on any process and you can contribute. Right? Either it can be a EDM or ECM or any other process. You can contribute by taking the application based workpiece and and you can see, you can correlate, means you can compare the results with the existing one. So, however, there is a lot of research scope in AFM process, especially in terms of developing a flexible cooling process, because every time when you are changing the workpiece, we need a separate tooling for fixing the workpiece and as well as for guiding the medium flow. So there is a big challenge. We can develop a flexible tooling and as well as the optimization of the process parameters is also important. So we can use various tools for optimizing the process, and we can do a lot of prediction on the developed processes. So that is also a research scope. These are the use.
Participants, if you have any doubts, you can get it clarified. You can unmute yourself and then ask the doubt. And if you have any technical issues to unmute yourself, you can even write your questions in the chat box. We will read it out. Okay, there is one question, sir. For which use this material is prepared?
For which?
Use, like what is the application mostly? In the chat box,
yeah.
Like I think when we are discussing about the abrasive flows, I think this question was popped up.
Yeah, which use this material is prepared? Means the media material you are talking about?
Mostly it would be the same.
Okay. So we
Media.
use actually viscoelastic material, which looks like a rubber. and also we mix that material with abrasive particles. What is the scope in this work? Yeah, there is a lot of future scope. Means one can, as I discussed, one can work on develop product development and process development in this area. One can work on optimization. One can work on developing a flexible fixture. This process. Any other questions?
Hello, sir.
Yeah. Yes. Tell me.
In case of spiral flow assisted abrasive flow machining,
Okay.
since the spinning of the drill bit is unidirectional, there may
Yes.
be a chance of formation of spiral imprints on the surface of the specimen, right?
Yes. Yes. Chances are there.
So, how can this be resolved?
Yeah, actually, maybe by controlling the RPM of the spiral rod. And another thing is actually there is a, of course, there is a gap between the drill bit and the workpiece, right? So the drill bit is fixed with the gear train, and we are using a motor, separate motor for rotating that spiral rod, right? So what they claim is actually the spiral behavior will give you helical fluid path and also the scooping flow, etc., which gives more interaction of abrasive particles with respect to asperities. So that is the idea, right? So whereas when you increase the speed, what happens actually is the spiral rod will act as a normal rod, means the scooping flow will not be happen. So that's why we need to have a control on the parameters, and that too, such problems you can explore only when you are practically doing it. Means you are developing a setup and working on it. Means while doing the pilot experimentation only, you will understand.
Okay, sir. Thank you, sir.
Akash, I think you can directly unmute yourself and ask. Like you have asked the question, how does it may affect day-to-day life? Can you be more precise and clear? Akash? Okay, your mic is not working. So there is a question like, how does it may affect the day-to-day life? Like I think maybe now this advanced machining, how does it affect day-to-day life?
How does it affect means actually in our day-to-day life we are seeing a lot of changes, right? In terms of change in materials, they are advancing everywhere in terms of technology, and we have a lot of new materials explode, means composites, and superalloys, etc., for various applications like heat treatment applications, and for lightweight and good strength and other properties for car bodies, etc. We are replacing various materials, right? So, however, these advancements in the finishing process also will have a crucial role. That's why we need to advance. We need to advance in this process as well, the finishing process as well. So how it will affect our day-to-day life? Uh, so the improvement in the technology, and for example, if you say the medical implants used in our body, so we'll have a lot of means there is a contamination problem actually generally when you do some secondary processes. So that's why we have a 3D printing, right? 3D printing will give you near net shape, and 3D printing is very much successful in medical applications. So like that, advancement in the process will have a lot of changes, lot of scope in the day-to-day life.
So one more question. What would be working pressure?
Working pressure
What would
will depends upon the setup you have developed. So in my case, actually, we have used the 30 bar to 50 bar extrusion pressure, and that is the working pressure. And the pressure will vary from the cylinder, and the pressure will vary from the fixture, the pressure may vary in the workpiece zone, etc. So these are the common levels of working pressure used in AFM are 30 bar to 50 bar.
I think that's it. Can we use it for materials?
Yeah, we can we can finish different types of materials. People are working on finishing of ceramics as well in this AFM. They are working on advanced materials like Inconel 718, Superalloys. They are working on finishing of composites. The major part is finishing. We can get a nano level finishing. AFM.
Okay, sir. Thank you very much, sir. Thank you for being with us and spending your valuable time. It was a very great informative session where all the micro nano machining has been introduced and explained very well. And thank you for your patience in explaining all the processes in a detailed manner by which the students and the participants would be able to understand it more clearly. And I would like to wholeheartedly thank Dr. G. Venkatesh Garu for his valuable time, because let me tell you, he's also the coordinator of one of the online program that NIT Warangal is organizing. So, in spite of his busy schedule, he has been so kind to accept our invitation and has spent his valuable time with us in explaining all the details of abrasive flow machining process, which is an advanced machining process. Mostly, which is, as he has explained, it is used in high-end components, especially in aerospace sectors. So it is a great session that we had today. And we'd like to once again thank Dr. Venkatesh for his valuable time and valuable inputs in guiding us in the field of advanced machining. Thank you, sir. Thank you for your
Okay.
kind gesture.
Thank you all. If anything is there, you can mail me. I will respond.
Yes, sir. Thank you very much.
Yeah, okay.
Thank you, participants. Tomorrow again in the morning at 10 o'clock, we'll meet you. Kindly fill your feedback forms before you leave the session. Thank you.